Hello there. In this video, I'm going to show you how you can model a very simple microprocessor using Python and test-driven development. The idea is to show you how you can implement in software a very simple microprocessor, and ideally you should already know how to program. Okay, so basically our simulated microprocessor is going to be a very simple thing. So basically, we are going to implement these four operations. So we are going to start with nope. Nope is no operation, so it doesn't do anything. Then I'm going to show you how you can implement and how does it work, the other instructions like move, increase, decrease, and conditional and unconditional jumps. Okay, so to start, we are going to create two files. So the first one, called simproc, is where we are going to implement our microprocessor model. We are also going to create a new file which will implement the tests. So let's start by creating our simple microprocessor. So in simproc, we are going to create so in this file we are going to start by create a class which we'll call simproc. So basically it's the class where we are going to model our simple microprocessor. We'll start by defining the constructor, and we'll have a function which we'll call debug. Okay, debug will allow us to debug the contents of our simple microprocessor. So before we start implementing more complex things, a base thing that so basically a microprocessor like we are implementing now doesn't do anything. So this is basically an empty shell for something. So to start, every all microprocessors at least have to have a memory, or have to be able to access memory. So we are going to start by saying that we have something called memory, okay, which is basically a Python list with at least 10 elements, okay? Just to test, let's say that we are going to have a very simple microprocessor which can handle 10 memory addresses, okay? So let's continue. So if we create now our main, basically we can create our microprocessor, and we at least can call debug. Okay, so let's run this, and as it's normal, it doesn't do anything. So let's start by implementing something on debug. So debug, it shows the contents of memory, of our microprocessor's memory. So basically let's just print self memory. Okay, so basically our empty microprocessor, as you can see, has all memory addresses set to 0. Okay, so let's implement a function called execute, which is supposed to be a function that receives an instruction, receives a set of arguments, and executes them. So basically executes is a method that executes an instruction. So basically, if we do to execute the nope instruction, it is supposed to do nothing, okay? So as you can see, although we still haven't said anything, a nope instruction doesn't execute anything, but let's just enforce that. So basically, if our instruction is a nope instruction, we just say pass, okay? So basically, it doesn't do anything. Okay, so basically we now have a very simple microprocessor, or a very simple model of a microprocessor that runs an instruction, at least runs one instruction called nope. So let's implement the tests. We start by importing unit test. Then let's import our microprocessor class, and let's define our class for the test, okay? So we are going to start by defining the setup function. The setup function on test-driven development, on Python tests, is where we prepare, is where we set up everything really that we are going to need to implement the test. So basically, I'm just going to create a microprocessor here as well, okay? And so the first test that we are going to do is test that an nope instruction works, okay? So basically the idea is, if I execute a nope instruction, at least it shouldn't do anything. So basically, after I execute the nope instruction, all the memory contents of my microprocessor should be equal to 0. So I'm going to do a very simple thing. I'm going just to add all the numbers in the memory, okay, in the memory of our microprocessor, and I'm just going to assert equal, okay? So basically, this test will pass if after I execute nope, the sum of the memory addresses, the sum of the contents of all the memories addresses is 0, okay? So let's run this thing, and okay, we have a test that passes. Great. So we have just implemented no operation. So this one is done. So let's going to implement now the move operation. So basically the move operation works something like this. So let's imagine that I have my memory, okay, which is a Python list, and the memory instruction works like this. So I do move, I have a destination, and I have a source. So basically, if I say something like this, to move to memory 0, or the position 0 of the memory, move value 10. So basically, if I do this, I'm just saying that on the 0 index of the list, I should have now a 10. If I say move to position 1 after this one, if I say, okay, now move to position 1, value 20, I should have a 20 on my second position, or position index 1, okay? So move, this instruction allows me to move a value to a memory address, okay? So let's start by implementing this on the test. So I'm going to test moving a value to memory. So basically, this is destination, this is the source. So I'm going to test moving a value to memory. So this works like this. So let's say that I execute a function that I call move to position memory position 0, and let's use the memory example 10, okay? Let's say that I move the value 10 to memory position 0. So now I have to assert that the memory of position 0 is 10, okay? So this is just my assertion. Let's run this, and as it's normal, it fails, okay? So basically it says that, as you can see here, it's failing the movement, the instruction move a value to memory. So how can we implement this? We go back to our microprocessor and we simply include the possibility to execute this function. So just if the instruction is a move instruction, okay, we are just going to, let's put it this way, destination source, okay, let me check if I'm doing list like this. So destination source, yeah, equals arg. So basically I'm deconstructing the tuple, the arguments to both these arguments. So now I'm just going to say that self, my memory of, I have to convert this. This is all strings that I'm passing. So basically all arguments, I'm assuming that all arguments for executing are strings and the memory stores integers, okay? So if I always assume this will always work fine. So basically I'm just going to put on the position that I send through on the destination, and I'm just going to say that the destination, the position that I'm sending to the destination equals to the integer of the source. So let's run my tests and everything works fine. So let me test here, run unit tests. So it works, 2 tests passed. So my microprocessor is now able to execute this instruction. Let me try here just to show you. Okay, so basically how this works, if I move, to position 0, value 10, okay, let me run this. So as you can see, the contents of my memory address 0 is 10. As by my example, if I move to position 1, value 20, okay, so now I have both memory positions with my values. Okay, so now I can set values on memory addresses. A thing that is also quite important is being able to move not values but value content. So let's memory reference. Let me give you an example. So let's say that I move 10 to position 0, but let's say that I now want to move to position 1, not the value, not, so basically I want this, okay? I want my memory to have 10 here and 10 on the second position, on position index number 1, okay? So I have 2 ways of doing this. The first one is, okay, moving a 10 to position 0 and then move another value 10 to position 1. But there is another way, or there is another thing that we can do, which is something like this. So what is this? This is how NASM assembly works. So basically what I'm saying here is I want to move 10 to position 0, and now I want to move the contents of memory address 0, okay? So the brackets now say that instead of moving 0 to position 1, I want to move the contents of memory address 0 to position 1. So when I do this, I have to have 10 on my both my memory areas. If I, for instance, say this, I want to move 20 to position 0, and then the contents of position 0 to position 1, I would have 20 on both memory areas, okay? So basically this is what we call a memory reference. So I'm instead of copying a value, to a memory address, I'm copying a value which is on the memory reference, okay, on a certain position of the memory. So how do we implement this first on test? So let's create a new test which we call test move memref. So basically I want to move a memory reference or a value which is somewhere on the memory to another memory position. So how can we implement this? We start by implementing the move. Okay, I'm going to use the same example. So basically, if I move a 10 to position 1 and then move to position move a 10 to position 0, and then if I move to 1 the contents of position 0, I'm expecting that position 1 is as a value 10. Okay, so let's run this. Okay, as it expected, um, this test is failing. So how can we implement this here? One thing I have to check if is this source is a value or a memory reference. So I'm just going to create here a very simple function that checks if a parameter is a memory reference. Okay, I'm just going to put it here to isolate it. So basically a parameter is a memory reference if the first element is a bracket. Okay, the first character is a bracket and the last character is a closing bracket. Okay, so just to test here, let's is memory reference. So for instance, a 10 is not a memory reference. Sorry, it's not this. So a 10 is not a memory reference, but the memory reference 10 is a memory reference. Okay. Other function that I'm going to need is giving, if I give to this function a memory reference, I want the value inside it. So basically, the idea is if I give this 10, I want this function to give me the number inside. So I just have to remove the start and the end bracket. So just going to return start from the first, so remove the first bracket and the last bracket. Okay. By the way, I can return, I'm going to use this to set a value, so I can just return the integer value of it. So now that I can identify memory references, I'm just going to need to check if the source is a value, okay, or a memory reference. Basically, if the source is a memory reference, I want the source to be the value on that memory position. Okay, so basically, if the source is a memory reference, like for instance, this is doing, like if I say, okay, I want my memory reference 0, okay, basically I want two things. Basically, I want to get the address 0 inside the brackets, which is what this thing here does. So it returns me the 0. Then I want to get the value which is on memory position 0, which by our tests is going to be a 10. Okay, so memory reference 0 is basically self.memory 0, which is going to return me a 10. Okay, so if source is a memory reference, I have to get the value which is on the memory. If not, we do it our old way. Okay, so let's start by running the tests to guarantee this thing works. Okay, sorry, run all unit tests. One still fails. Let me check. sorry, I'm doing the source here. Uh, I'm just going to need this. Okay, so basically I'm here converting the source and using this, so the test should work fine. Okay, it works fine now. Okay, but let's see here through our debugging how this works. So if I move a value 10 to position 0 and to position 1, the contents of 0, okay, of memory address 0, okay, if I run this, as you can see, we have both values here. I could say, okay, move to position 2 the contents of 0, okay, and now we have on position 2 the contents of 0. So our move instruction is getting better. Okay, so now we are now able to move things around memory, okay, but most microprocessors have um, certain specific memory areas that we call the registers. Okay, the registers are usually small caches on the microprocessor that we are usually used to store temporary values and doing comparisons and things like that. Okay, so basically we are going here to create um, a register that we're going to call R0. Okay, so basically R0 is going to be a register. Let's set it to 0, sorry. And one thing that we also can do with the move operation is that we can move values to memory addresses, okay, but also to registers. So basically I can move a value, okay, a value to a register. So let's do it, okay. Let's start by implementing the test, okay. So test of moving to register a value. So how is this is going to work? So let me copy this part here. Okay. So it's simple. It's simple. If I move a value 10 to register 0, okay, I'm expecting that the value of the register is set to 10. Okay. So if I move 10 to R0, I'm going to expect that R0 as register 0 as value 10. So let's run these tests, and as expected this test is failing. So it's a very simple change that I have to do here. Okay, so basically the only thing that I need to do is check the destination. So here, so far I've been assuming that the destination is a memory area, but now I just need to check. Okay, so if the destination is an R0, I just need to set. Sorry, I just need to set R0 to the integer of the source. Okay, if else, okay. So if I'm not setting the register value, I'm setting a memory value. So this should work. Let's test. Okay, and okay, we now have our test. So let's see how this works. Let me just put something here on debug, okay, just to print the contents of R0, okay, and like this, R0, and basically if we move a value, let's leave it this way. If I move a value of 10 to R0, sorry, this runs tests. Okay, as you can see, R0 has value 10. One thing that I want to make sure that it works is I can move a value to R0 to register 0, but I can also move a memory content, so a memory reference. So I'm setting memory position 0, I'm setting the value of 10, Then here I'm moving the contents of memory position 0, which is the number 10 that I've written here. I wanted to move to R0. So first let's see if it works. Okay, as you can see it works. If I change this to 20, okay, it keeps on working. But just let me make a test. Okay, I'm going to reuse this same test here with some small changes. So I want to move a value to position 0, then I want to move the contents of position 0 to R0, and then I'm expecting that R0 has a 10 there, okay? So let's run it, and it should work fine. Sorry, this is same value. Register memory reference, okay? Okay, 5 tests and they all work fine. So basically, this this test here all make sure that our move instruction is working fine. Okay, so we have implemented the move instruction, so we can now move values to memory or register and from memory. We also could implement a move, something like this: move from R0 to position 0, position 1. But okay, let's skip it. This is working fine, so let's move on. Now let's going to implement uh, these quite simple operations, which is the increase and decrease. So how do this work? So imagine that we have all memories zeros, okay? And I say something like this, okay? Increase the value in position 0. So when I do this, I'm expecting the value on position 0 to increase. So this is a memory area. Just like I said, the move, okay, on the move instruction. This basically is increase a destination. So as I said, if we increase 0, it sets 1. If I do an increase 0 again, so it sets the value to 2. Then if I say, okay, decrease position 0, it gets back to 1, and another decrease, it goes back to 0, okay? So this is increase and decrease memory areas, okay? Let's start by implementing the tests. So let's test increase memory area. Let me see, yeah, memory area. So very simple thing. If I say, okay, increase position 0, okay, increase the value in position 0. Let me copy here this assert. I'm expecting that position 0 now has the value 1, okay? So it, as I said on the beginning here, just to clarify, all the memory contents are set to 0 on the beginning, okay? So if I say increase the value in position 0, okay, the value has to be 1. Let's run, and as expected, the test fails. So let's implement this instruction here on the execute. So I'm going to be a little bit pragmatic here. I'm going to join both increase and decrease instruction on the same area of the code, okay? So basically, if the instruction is an increase or a decrease, okay, we are talking here about um, increments and decrements. So I'm saying increase, decrease, it's increment and increment. Here I'm talking about move instruction. So very simple. If the instruction is an increment, okay, what do I want to do? I want to increase the value first. I just want to say this, okay? So I have to get my destination from the arguments. So, and then I'm going to say that, okay, so the content of the memory address on that specific destination, on that specific address, let's put it this way, is going to increase by 1, okay? It'll just, yeah, it's just this. It's going to increase by 1. Okay, let's see if our test runs fine. Okay, as you can see, the test is working fine. Okay, so we have implemented increase the memory. Um, Now we can try to implement the decrease. Okay, let's say if I say decrease position 0 before. I don't want negative numbers, although it could work. But let's start by saying, okay, I want to move to position 0. I want to move the value 2. So basically, after I decrease the value there, it should have a value of 1. So I set value 2. I set value 2, something like this. So as explained here, I set value 2 here, and after decrease 0 or memory area 0 or memory index 0, I should have a value of 1. Okay, so let's implement, let's run the test. So as expected, the test is failing, and I'm going to implement here our decrease. Okay, and just say that it's subtraction. Okay, let's see if the test runs, and as you can see, now the tests are working fine. So just to for you to check, or for you to see how this is working, so if I increase position 0, okay, so I set the position 0, memory position 0 to 2 here, and then I increase, I should have a 3. As you can see, I have here my 3. And if I decrease the position 0, I should have a 1. Okay, so I have put it there a 2. I decrease it, I should have a 0. Okay, so great. I should also be able to increase, okay, as I can increase and decrease memory areas, I also should be able to increase and decrease registers. Okay, so first of all, I'm just going to do a very small change here, which is, as I'm filtering increase and decrease here, basically in this area of the code, I know that either is an increase or a decrease operation. So I'm just going to move this to a one-liner. So on one-liners in Python, it works something like this. True A if something else B. So the idea, this is how one-liners in Python work, which is if X is true, this evaluates the contents of A, else evaluates the contents of B. So how this works here. So basically I'm just saying that um, the contents of the memory by the contents of the specific memory address will increase by 1 if instruction is the increase, okay, else will increase by -1. So just this is just a very this is syntactic sugar, a very small change, but I'm just saying that if the instruction is increase, I'm adding a positive 1, or okay, a positive 1. I'm adding a 1. If not, I know that is a decrease, I'm decreasing it. Okay, so let's just check that this works, and as expected, the tests continue to work. Okay, um, and why did I change that? I did change this because I want to be able to increase and decrease also registers. So for instance, let's say that I do have something like this. So I move to R0 a value of 2. If I decrease R0, R0 should be set to 1, okay? And same thing, if I increase R0, I set 2, increase R0, should be 3, okay? So let's implement both tests. Let's reuse both these tests here. Let's start by increasing the register, okay? Okay, let's increase R0, and R0 should be 1 after the increase. Then if I move to R0 the value of 2 and decrease R0, R0, then my register should be set to 1, okay? Let's run this. And as you can see, both tests are failing. So because I'm assuming here that increase and decrease operation are always affecting the memory area. So I just need a very small change, which is if the destination is register 0, I do something, else I change the memory. So it's very simple. I'm just copying this and to say, okay, if the destination is not a memory area but is the register, I'm affecting only R0, okay? Let's run the tests and they continue to fail. Let me see what's happening here. Sorry, and forgot here self.mp, the object, the real object, okay? So the tests now are working, okay? So far we have been able to implement a very specific increases and decreases instructions. So these ones are all working fine now. So now we have what we call the conditional jumps, which are two instructions called jump if not 0, a jump if 0. So basically um, these jumps basically work with code, with a program. So let's imagine that you have a program that is running, and then you want to test if a certain thing is 0 or not 0, and if according to that condition or according to that value or the value of something, you want to jump to another area of your program. Okay, so now we are going to talk a little bit about programs in our microprocessor. So our microprocessor now is a very simple thing that just executes simple instructions, one followed by the other. So there's still no concept here of a program. So let's fix this. Let's create here what we call, let's create here a new list uh, where we are going to store a program, okay? So basically a program is going to be a sequence of instructions which will be on the list. So basically now what we are going to do is our program is going to be simple things like, okay, on the first instruction I'm going to move the 10 to position 0, and then let me write it like this, and then I want to have my second instruction which is going to move to a value 20, for instance, to position to the R0, and then I have my third instruction that is going to do another thing like another move or increase value R0, things like that. So as you can see, basically I'm building here a list of instructions. So my program or our program is going to be a list of instructions. So one thing is now relevant. So how do I know which line of the program I am executing or I have already executed? Okay, so there's this concept. There's this concept of special registers on the microprocessor, which there's a specific register that we call the instruction pointer. Okay, so basically the instruction pointer is going to be is going to have the value of which instruction we are now able to execute. So for instance, if my instruction if my IP, my instruction pointer is 0, it says that okay, I have to execute the instruction number 0, and then okay, and then I move my instruction pointer to the next value, and then my next instruction is this one, and then my next instruction is this one. Okay, it it I wouldn't need to have something like this if I only needed to execute the program from the beginning to the end. But so let's imagine that here I do something called a jump, and I said okay, now I want to jump to doing the instruction number 0. So as you can see, if I use this I instruction pointer and if I manipulate it, I I I, I use it to change the next instruction. So basically, as you can see, if I use this to move on my program, um, every time my program reaches this position, in this says, okay, jump back to this to position 0. So this is an infinite loop. It's always here. So it's a very bad program, but it works. So it's a program that is always on a loop. Okay, so I run instruction 0, I run instruction 1, I run instruction 2, and then instructions 3 says, okay, go back to instruction 1, 0. So 1, 0, 1, 2, 3, back to 0, 1, 2, 3. But this will allow me to build more complex programs. So let's implement how we can now build an execution engine on this microprocessor. So we are going to start to do a very simple thing, which is load. Okay, so basically load our load function or method loads a program. Okay, and in a simple way. I want my program to be a sequence of instructions. It's going to be a string, okay? My program is going to be a string. So basically, I have to do something like this, okay? But I have to split it on each enters, okay? So let's start by this, okay? So instead of executing this, I want to be able to load programs, okay? So basically, my first program could be something like, okay, move to position 0, move to position 0 value 10, okay? And then move to position 1 value 20, something like this. So if I run this, okay, it won't work, it won't do anything. But I want to parse all these instructions and put it on a list, okay, on a list of strings. So basically, this code here, this code list, I want it to be a list with all these simple instructions, each one on a position of the list. So let's start by okay. Let's start by saying that okay, our code. Um, let's start by stripping the first the empty spaces. Sorry, the empty spaces. So if I do this, okay, as you can see, it strips the first and the last empty spaces. Now, the second thing that I'm going to do is say that the code is going to be. I want code to be to split it. I want to split it. I want to build a list. Okay, let me put it as way. I want to split it by new lines. So if I work with this, okay, now I have each instruction on a string, but there's still some empty spaces here that I want to strip. So I'm going to say that I'm going to use this with this is syntactic sugar for which we in Python is called list comprehension. So I'm going to say that line for line in okay, this is a list comprehension. I'm saying this for each line in in this list, okay, in this list, I want to strip it as well, okay. So if I do this, okay, now I have each instruction correctly stripped and on each list element. Okay, so this works. Let's say just that my code here is going to be this thing here. Okay, doesn't do anything yet. Okay, so this is just a method to load a program on my microprocessor. So now we have to build support for run. Okay, so basically after I load the program, I want to execute it. I want to run. So this run runs the program. So how does this run works? And this is how microprocessors work as well. So basically the idea is something like this. So um, just a pass. While there's code, okay, while there's code, while there's code available, while we still haven't reached the end of the program, what do I want to do? So I want to get, okay, this still doesn't work. So I want to fetch the next line, okay, the next line of the program. I want to decode the next line, okay. So I want to fetch the next line. I want to decode it to see which kind of instructions is there, and then I want it to execute the function. So basically, the execution of a program is split in these three components. While we haven't still finished our program hasn't ended. You want to get next line, decode it, and executed it. Okay, so how can we work this thing out? We're going to start with this fetch. Okay, so basically fetch um, is going to retrieve the next line, the next instruction in the sequence, in the code sequence in our program. So let's implement here the fetch. So basically fetch fetches the next instruction. Okay, so if fetch is a very simple thing. So we have this instruction pointer, and that is why we are using it. This instruction pointer is like the counter which says which instruction is the next one. So basically I'm going to get the instruction which is on a certain position, okay, on the certain position given by this instruction pointer. I want to get that line. Then I want to increase the instruction pointer, okay. I want to increase it by 1, and then I want to return the line. Okay, so how does this work? Let's see here. So if I have this application here, this program that has two instructions, okay, the first fetch, the first fetch returns the first instruction, okay, while the second fetch returns the second instruction, okay. By the way, let's add here the instruction pointer as well to the debug, which we're going to use to prove that it is increasing. So after I do 2 fetches, okay, my instruction pointer is set to 2. Of course, if I do another fetch, I get out of the list of instructions, so I shouldn't do this. So our fetch is working fine. The next is the decode instruction. Basically, the decode instruction, which also exists on a real microprocessor, is the instruction, or is the step where we grab the instruction and try to understand which instruction is it inside. Since in this model each instruction is a string, and our execute separates the instruction from the arguments. The decode is going to be the function that separates the line. Okay, so basically, what I want to do is, if I have this instruction here, I want I want to separate the string move from the string r02. So I want to have the instruction to be the string move and the arguments to be a list made of, in this case, r0 and 2. Okay, so my decode function is going to be the one that splits this string in these two components here. So let's start by building our decode function. Okay, decodes an instruction here, and let's do a very simple thing. Okay, first of all instructions are like this. Okay, so we have the instruction, all instructions are like this. We have the instruction and we have a instruction split and arguments. So for instance, we have um, move destination source. Okay, we can have here a space or node. Okay, or we can also do increase r0. So there's always this empty space here that we are going to use to split the left side from the right side. So let's find where the first empty space here. Okay, oh, so I need to decode a line, of course. And okay, so basically the instruction is everything up to the separator. Okay, and the arguments are going to be everything after the separator. Okay, so basically this is something like this to the end. Okay, so from 0 to the separator, from 0 to the first empty space, it's the instruction. From the empty space to the end, okay, are going to be the arguments. Let's see if this split function is working fine now. Okay, sorry. And let's see if we do comment here. Okay, and b.decodes. Let's see if, okay, something like this. Let's see if it works. So as you can see, it's splitting the move from the rest of the arguments. Okay, but as I said previously, I want this right side here not to be a string like it is, but to be a list of strings. So I just need to go to our decode and say that the arguments are going to be arg for arg in args. So if I do this, if I run this now, as you can see, it's now splitting. So it's now splitting by character, but I don't want by character. I want to split it by the comma. Okay, so all my arguments on the right side should be split by the comma. So if I do this, now I can split it by the comma. And the only thing that I still need to do is clean these empty spaces here. So I just need to strip the argument. Okay, and as you can see, now I have my instruction and the list of arguments. So my decode function just needs to return this. And finally, we have the execute function, okay, which it's already implemented. So let's just write this on real Python instructions. So how do we know if basically now I need to write the while. So how does the while work? So as I said, we have this special variable here which is called instruction pointer, which says, okay, which is the next instruction. So basically, if my instruction pointer is still less than the length of the code, okay, basically if I still have code that could be executed, I want, sorry, here. So I want to get the next line, okay. I want to parse it by the instruction arguments, I want to decode it. Okay, self.decode line, and then I just need to execute it. Okay, so just with the instruction and the list of arguments, and I think this should work now. Let's try it. Let's still have the debug here. Let's try to run this. So basically I'm setting 10 to register 0 and 20 to memory position 0 and 20 to memory position 1. Let's see. Let's run this. Okay, as you can see, I have now a working application. Let's try to move to R0 the value of memory position 1, okay? And as you can see, R0 is set to 20. So I have now a working, I have changed the architecture of my microprocessor model to be able to execute functions, okay, to execute programs. So let's go back to as we were to jumps, okay. So conditional jumps, as we have now implemented a way of getting the fetching instructions. So we get as we now have the list of our code, and we have the instruction pointer which says, okay, what is the next instruction that should be fetched. So jump zero, jump not zero, jumps should work with that instruction pointer. So the idea is something like this. The idea is I'm going to be very pragmatic, and this jump works with like this. So I'm going to give an example. Let's suppose that I move let I move 10 to register R0, and I'm just the jump instruction basically is going to do something like line. Let me put this. So the idea is that the jump 0 instruction is going to test if R0 is equal to 0. If this is true, the instruction pointer is going to be set to the value in line, okay? In this case, since R0 is 10, this part will fail, so this won't turn out to be true. The jump is not jump if not 0 is the opposite. So the jump is not 0 is going to test if R0 is different 0. If this is true, it will jump to the next instruction will be set to the one on a certain line, okay? So let's build the tests for this first. So let's build the test. Let's test jump if not 0, okay? So jump if not 0 works like this. So let's set, as I said, so the jump instructions they depend on the value of register 0. So if the jump is not 0, should jump if the value of R0 is not 0, okay? Or if the value of the register is not 0. So if I set the value to 1, okay, and then I execute jump not 0, for instance, to position 10, okay? So if I say, okay, jump to position 10, jump to position 10 if R0 is different of 0, so jump if not 0, I want to assert, okay, that the instruction pointer is set to 10. Basically, I want to jump if R0 is not 0, I want to jump to line 10. If this is true, it should jump to line 10. The instruction pointer should be set to 10. So let's run the tests. It should fail, okay? So let's implement here the instruction. This is the conditional jumps. and it's very simple. So let's get the argument. Okay, let's get the destination, and it's very simple. So if the instruction is jump if not 0 and r0 is not 0, okay, so the instruction pointer should be set to the value of the destination. Okay, let's run the tests, and as you can see, it works. Okay, so the jump if 0 is quite similar. Okay, the jump if 0 tests if the value on the register 0 is 0. So basically I want to test this. So if I move a 0 to the R0 and then I say jump, if that value is 0, it should jump. It should jump to position to. It should set the instruction pointer to value 10. Okay, so let's run it. It should fail. So we just have to change here. So if the instruction is a jump if 0 and R0 is in fact 0, okay, we do this. Let's run the tests and it should pass. Okay, so conditional jumps are working. Finally, we have what we call the unconditional jump. The unconditional jump is very simple. If somewhere on our code we say, okay, jump to position 10, it jumps to position 10. There's no if. Okay, it's an unconditional jump. Let's just implement and test. Okay, so test jump. It's very simple. If we execute, I'm going to copy this. So if we say jump to position 10, it should set the instruction pointer to position 10. Okay, let's run it. It should fail, of course. Let's add it to here. Jumps. Okay. Else. Okay. So if it's just not 0, let me do this. I don't want surprises here. Okay. So if it's not any of these instructions, so do it the jump. So okay, as you can see, all tests are working fine. Okay, and we have implemented all our instructions. So with this said, we can now implement some programs. I don't have much time to implement. I'm going to head to my GitHub, or going to add some programs after this, but I'm just going to show you a very simple program. So I want to do a program that adds the first values on the memory. I'm going to give an example here. So for instance, imagine, let me remove this. Sorry, I don't do this. I want to remove this. Okay, so for instance, let's say that I have a value of 5 on the first position here, and I have a value of 3 on the second position, and I want to add, okay, I want to add these two values here using only the instructions that I have. Okay, so the program is going to be very simple. 5 plus 3, okay, is the same thing as 6 plus 2, okay, which is the same thing as 7 plus 1, which is the same thing as 8 plus 0, okay. So as you can see, this is a very simple thing. So I'm basically incrementing the value on the position 0, and I'm decrementing the value on position 1. So basically my program is going to do a very simple loop which will increase this element here, okay, will increase this element here, will decrease this element here until this element reaches 0. So I have move instruction, so I can move values to position 5, position, sorry, I can move value 5 to position 0, value 3 to position 1. I have instructions also to increase value, so I can increase this 5 to 6. I have also instructions to decrease, okay? I can decrease this. And I also have now an instruction which allows me to check, the, to jump, to be able to jump if the value is 0 or not 0. Although I test the value of a register. So let's start by doing a very let's start by simulating this program without the loop. Okay, so I'm going to start to move a 5 to position 0 and a 3 to position 1. Okay, let me run this, and as you can see, my memory has the values. Okay, so basically if I increase the value in position 0 and decrease the value position 1, okay, now I have a 6, I have a 2, okay, I have 6 on the first position, on the 0 position, and 2 on the 1 position. Okay, so I have to repeat this until I have a number 8 and a 0 here. So I just want to eliminate this part here. So it's a very simple. I increase the value on the first memory area. I decrease the value on the first. Now I just need to check, okay, on this value, this value here, is it already 0? So if it's true, if it's not 0, I want to continue the increase and decreases, okay? Although if it's 0, I want to end the application. So I just need to test if this value is 0 or not. So it's very simple. I just need to, as you know, my jump instructions check the value on the register. So I just need to put on the register 0 the contents of position 1. Okay, so I want to copy the values that are here to the register, and now I want to test. Okay, if it's not 0, I want it to go back to this line here. So this is line number 2. Okay, so I'm going to run this, and as you can see, it's working. It's doing the sum. Let's put it here, 5 plus 6, it should be 11. Okay, so as you can see, it works. So I'm going to repeat. This is line number 0. Okay, this is line number 0. This is line number 1, line number 2, etc. So basically what I'm doing here, I'm setting values on the first positions, and then I'm increasing the first value and decreasing the second value until, and I'm repeating this while the value here is not 0. Okay, so I'm jumping back to this instruction here while I still have value, while I don't have a 0 value on this position here. So as you can see, it runs perfectly fine. Of course I could implement a test to make sure that this always works. As I can give here more numbers. Okay, 19 plus 19 should be 180. So as you can see, I have way I have enough instructions to do very simple things on my microprocessor. So okay, so I have jumps, I have lots of instructions. I've shown you how you can implement tests, okay, to make sure that everything you do, you don't break after, okay. I've also shown you how these instructions work, okay, which instructions are these. Um, I've also talked a little bit about this run method, okay, the run method. Um, it's quite similar to what a real microprocessor does in hardware. So it gets the next instruction, it decodes it. Not, of course, a real microprocessor won't do string manipulation, but mine we will do byte manipulation, and then it executes the function. Okay, the real thing, or the most important thing here regarding regarding running a program is this instruction pointer. Okay, so this instruction pointer always returns the next instruction on the pipeline, and this is very relevant because um, because if we have these jump instructions, we can move that instruction pointer so that we can have running programs. Okay, so this was a very simple, although a little bit lengthy approach, or a very lengthy approach on how you can implement how you can model a very simple microprocessor in Python, okay, in code, okay, and then I hope you have learned something. Okay, I've shown you also a very simple program to add two numbers. Of course, I could also do a program to decrease. Okay, so very simple. How could I change this to decrease? It's very simple. So 8 minus 5 is the same thing as 7 minus 4, as 6 minus 3. Okay, so basically to subtract, instead of increasing the first one, I decrease the second one. So 8 minus 5 is 3. Okay, so a very simple program to add and a very simple program to subtract. You can also have programs to multiply. Okay, you can do a multiply as a sequence of sums. Okay, and you can also do a program to find the maximum value of 2. Okay, so the maximum value 2 is very simple. You just subtract values until one of them reaches 0, and then the first one to reach 0 is the minimum. Okay, so the other is the maximum. You just have to take care that you store the original numbers somewhere. Okay. Okay, I think I could do this. So let's do a program to find the minimum of 8 and 5. So let's store the values on other places of memory. Okay, so let's keep the original values on other positions of memory. Now we are going to decrease the value in position 2 and value position 3 until one of these is 0. So basically, first we're going to test if we reach 0 here. Okay, if the number 2 has a 0. Okay, then we're going to test if position 3 has reached. I have to change this, sorry. So first I'm going to decrease position number 2, okay, then decrease position 3, then I'm going to test which one has first arrived to 0. Okay, if none is 0, I'm going to jump back to the decreases. Okay, so this is 0, 1, 2, 3, 4, line 4. Okay, so if there's no one 0, I'm going to go back here to keep decreasing. I'm going to keep decreasing until one of them is 0. So if it's this one here, I'm going to say that the minimum is the one in position 0. Okay, and then jump to the end, whatever it is. Else I'm going to say that, okay, move our 0, the value 1 is the minimum. Okay, and then this is the end. So sorry to be so brief. Okay, so basically, if the minimum is the one that reaches 0 is the one on position 2, I want to jump to here. Okay, so this is line 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, this is 11, and if it's this one that is 0, so 11, 12, 13, 13, 13, and in this case I'm going to jump to 14. Okay, let me see if this works. It may not work. Okay, yeah, it's saying the minimum. In this case, the minimum of number 8 and number 5, it's number 5. Okay, if I invert this, it keeps on saying that it's number 5. Okay, it's number 5. uh, how could we change this to find the maximum? Okay, to find the maximum will be just saying, okay, instead of one of them being the minimum, it's saying, okay, it's not that this one is the minimum, it's the other one that's it's the maximum. So the maximum of 8 and 5 is going to be 8. Okay, and then if I switch this around, okay, it says still that it's 8. Okay, so it's a very simple program um, to find minimum and maximum of two values in memory. Okay, so thanks for watching.